Hello everyone. Today's topic is Chapter 15 Hazardous Waste. Environmental engineers design systems to manage hazardous waste properly and consider the impacts of designs on the end-of-life management. What is so amazing in retrospect is the total nonchalance with which the American people tolerated the disposal of highly toxic wastes ever since industry first started producing such materials. Open dumps, huge waste lagoons, blatant dumping into waterways, all this existed for decades. Only since the early 1980s, however, has the public become conscious of what such indiscriminate dumping can do. Since then, we have made heroic efforts to clean up the most odious examples of environmental insults and health dangers and to regulate industry so as to prevent future problems. 15.1 Defining hazardous waste. A hazardous substance is defined in the United States by the U.S. EPA as any substance that because of its quantity, concentration, or physical, chemical, or infectious characteristics may cause or significantly contribute to an increase in mortality or cause an increase in serious, irreversible, or incapacitating reversible illness or pose a substantial present or potential hazard to human health and the environment when improperly treated, stored, transported, or disposed of, or otherwise managed. Hazardous waste is a name given to material that, when intended for disposal, meets one of two criteria. Table 15.1. It contains one or more of the criteria pollutants or those chemicals that have been explicitly identified listed as hazardous. Over 50,000 chemicals are thus identified. The waste can be defined by laboratory tests to have at least one of the following characteristics: flammability, reactivity, corrosivity, toxicity. Flammable materials are defined as those liquids with flash points below or those materials that are easily ignited and burned vigorously and persistently. Corrosive materials are those which, in an aqueous solution, have pH values outside the range 2.0 to 0.5, or any liquid that exhibits corrosivity to steel at a rate greater than 6.35 mm per year. Reactive wastes are classified as unstable and either can form toxic fumes or can explode. The greatest difficulty in defining hazardous waste comes from establishing what is and what is not toxic. Toxicity is almost impossible to measure. Toxic to which animals or plants? What concentrations over what time periods? The U.S. EPA defines toxicity in terms of four criteria: bioconcentration, LLC, toxicity. Bioconcentration is the ability of a material to be retained in animal tissue to the extent that organisms higher up the trophic level will have increasingly higher concentrations of this chemical. Many pesticides, for example, will reside in the fatty tissues of animals and will not break down very quickly. As the smaller creatures are eaten by the larger ones, the concentration in the fatty tissues of the larger organisms can reach toxic levels for them. Of most concern are aquatic animals and birds that feed on fish, such as seals and pelicans, as well as other carnivorous birds such as eagles, falcons, and condors. LD, a measure of the amount of a chemical that is needed to kill half of a group of test specimens, such as mice. The animals in a toxicity study are fed progressively higher doses of the chemical until half of them die, and this dose is then known as the median lethal dose, 50% or LD. The lower the amount of the toxin used to kill 50% of the specimens, the higher the toxic value of the chemical. Some chemicals, such as dioxin and PCBs, show incredibly low LDS, suggesting that these chemicals are extremely dangerous to small animals and other test species. There are, however, some serious problems with such a test. First, the tests are conducted on laboratory specimens such as mice, and the amount of the toxin that would produce death in humans is extrapolated based on body weight, as illustrated in the example below. This is a shaky conclusion, however. First, the physiology of a person is quite different from that of a mouse, so a person may be able to ingest either more or less of a toxin before showing adverse effect. Second, the effect measured is an acute effect, not a long-term, chronic effect. Thus, toxicity of chemicals that affect the body slowly over years is not measured, since the mouse experiments are done in hours. Finally, the chemical being investigated may act synergistically with other toxins, and this technique assumes that there is only one adverse effect at a time. As an example of such problems, consider the case of dioxin discussed in Chapter 14, which has been shown to be extremely toxic to small laboratory animals. All available epidemiological data, however, show that humans appear to be considerably more resilient to dioxins than the data would suggest. Example 15.1. A toxicity study on the resistance of mice to a new pesticide has been conducted, with the following results. What is the LD of this pesticide for a mouse? What is the LD for a typical human being weighing 70 kilograms? Assume a mouse weighs 20 grams. A is at the concentration at which some chemical is toxic, and this is used where the amount ingested cannot be measured, such as in the aquatic environment or in evaluating the quality of air. Specimens such as goldfish are placed in a series of aquariums, and increasingly higher concentrations of a toxin are administered. The fraction of fish dying within a given time is then recorded and the LC is calculated. As a rough guideline, a waste is considered toxic if it is found to have a AEV less than 5 mg by weight, or if the LC is less than EEG. Finally, a chemical is considered toxic if it exhibits phytotoxicity or toxicity to plants. Thus, all herbicides are, by this definition, toxic materials, and when they must be disposed of, they must be treated as hazardous wastes. A final criterion for being hazardous is if the material is radioactive. Radioactive wastes are, however, handled separately and are governed by separate rules and regulations. Radioactive waste management is covered in Section 15.3. One concern in hazardous waste disposal is the speed with which the chemical can be set free to produce toxic effects in plants or animals. For example, one oft-used method of hazardous waste disposal is to mix the waste with a slurry consisting of cement, lime, and other materials, a process known as stabilization solidification. When the mixture is allowed to harden, the toxic material is safely buried inside the block of concrete from which it cannot escape and cause trouble. Or can it? This question is also relevant in cases such as the disposal of incinerator ash. Many of the toxic materials, such as heavy metals, are not destroyed during incineration and escape with the ash. If these metals are safely tied to the ash and cannot leach into the groundwater, then there seems to be no problem. If, however, they leach into the water when the ash is placed in a landfill, then the ash would have to be treated as a hazardous waste and disposed of accordingly. How then is it possible to measure the rate at which such potential toxins can escape the material in which they are presently embedded? As a crude approximation of such potential leaching, the EPA uses an extraction procedure where the solidified waste is crushed, mixed with weak acetic acid, and shaken for a number of hours. This process is known as the toxicity characteristic leaching procedure, TCLP. Once the leaching has taken place, the leachate is analyzed for possible hazardous materials. The US EPA has determined that there is a list of contaminants that constitute possible acute harm and that the level of these contaminants must not be exceeded in the leachate. Table 15.3 includes a few such chemicals. Many of the numbers on this list are US EPA drinking water standards multiplied by 100 to obtain the leaching standard. 15.2 Hazardous waste management. Hazardous wastes are controlled in the United States by the US EPA. This mandate is under one of several pieces of legislation, most notably the Toxic Substances Control Act (TSCA) of the Comprehensive Environmental Response, Compensation, and Liability Act (CERCLA), its amendment, the Superfund Amendments and Reauthorization Act (SARA) of the Resource Conservation and Recovery Act (RA) and its amendment, the Hazardous and Solid Waste Amendments (ISUU). TSCA is aimed at preventing the creation of materials that may eventually prove damaging or difficult to dispose of safely, whereas RCRA addresses the disposal of hazardous wastes by establishing standards for secure landfills and treatment processes. RCLA is directed at correcting the mistakes of the past by cleaning up old hazardous waste sites and is usually referred to as Superfund because it set up a large trust fund paid for by chemical and extractive industries for the purpose of providing resources to clean up abandoned sites. The US EPA uses these funds to address acute problems due to improper hazardous waste disposal or accidental discharge and the cleanup of old sites. 152.1 Cleanup of old sites as part of the Superfund program. The US EPA established a National Priorities List (NPL) of hazardous waste sites that are in need of immediate cleanup and are eligible for funding under RCLA. Estimates of the number of these sites vary, but there are tens, if not hundreds, of thousands of sites in need of some degree of cleanup at a cost of millions to billions of dollars. The NPL still includes about 1,100 non-federal sites that are in immediate need of attention. As of this writing, about 980 total sites have been cleaned up. Because of the large number of potential Superfund sites, the US EPA has developed a ranking system so that the worst situations can be cleaned up first and the less critical can wait until funds, time, and personnel become available. This hazard ranking system ARS tries to incorporate the more sensitive effects of a hazardous waste area, including potential adverse health effects, the potential for flammability or explosions, and the potential for direct contact with the substance. These three modes are calculated separately and then used to obtain the final score. Being conscious of public opinion, the scores tend to be overwhelmed by situations wherein human health is in danger, especially for explosive materials stored in densely populated areas. The potential for groundwater contamination in areas where water supplies are from groundwater sources also receives priority status. This technique minimizes the criticism often faced by USEPA that they have not done enough to clean up the Superfund sites. They have, in fact, tackled the most difficult and most sensitive sites first and should be commended for the rapid response to a problem that has been festering for generations. In addition to the USEPA list, the Department of Energy has about 160 sites that require cleanup, and the Department of Defense has thousands more. The Department of Defense itself has spent billions of dollars on cleanups. Much of this is the legacy of nuclear weapons testing and manufacturing because many of these facilities were strictly secret, and the contracting operators could do almost anything they wished with the waste. The states also have lists of sites to be remediated. New Jersey's Jersey City Chromium site was discussed in Chapter 1. The type of work conducted at these sites depends on the severity and extent of the problem. In some cases, where there is an imminent threat to human health, the USEPA can authorize a removal action, which results in the hazardous material being removed to safe disposal or treatment. In less acute instances, the USEPA authorizes remedial action, which may consist of the removal of the material or more often the stabilization of the site so that it is less likely to cause health problems. For example, in the case of the notorious Love Canal in Niagara Falls, the remedial action of choice was to essentially encapsulate the site and monitor all groundwater and air emissions. The cost of excavating the canal would have been outrageous, and there was no guarantee that the eventual disposition of the hazardous materials would have been any safer than leaving it there. In addition, the actual act of removal and transport might have resulted in significant human health problems. Remedial action, therefore, simply implies that the site has been identified and action taken to minimize the risk of having the hazardous material cause human health problems. In the most common situation, some chemical has already contaminated the groundwater, so remediation is necessary. For example, a dry cleaner may accidentally or purposefully discharge its waste cleaning fluid, and this may find its way into a drinking water well for a nearby residence. Once the problem is detected, the first question is whether or not the contamination is life-threatening or if it poses a significant threat to the environment. Then a series of tests are run using monitoring wells or soil samples to determine the geology of the area and the size and shape of the plume or range of the contaminated area. Depending on the seriousness of the situation, several remedial action options are available. If there is no threat to life, and if it can be expected that the chemical will eventually metabolize into harmless end products, then one solution is to do nothing except continued monitoring, a method known as natural attenuation. In most cases this is not so, and direct intervention is necessary. Containment is used where there is no need to remove the offending material and or if the cost of removal is prohibitive, as was the case at Love Canal. Containment is usually the installation of slurry walls, which are deep trenches filled with bentonite clay or some other highly non-permeable material, and continuous monitoring for leakage out of the containment. With time, the offending material might slowly biodegrade or chemically change to a non-toxic form, or new treatment methods may become available for detoxifying this waste. Extraction and treatment is the pumping of contaminated groundwater to the surface for either disposal or treatment, or the excavation of contaminated soil for disposal or treatment. Sometimes air is blown into the ground and the contaminated air collected. The characteristics of a hazardous chemical often determine its location underground and therefore dictate the remediation process. If the chemical is immiscible with water and is lighter than water, it most likely will be floating on top of the aquifer, as shown in Figure 15.3a. Pumping this chemical out of the ground is relatively simple. If the chemical readily dissolves in water, however, then it can be expected to be mixed in a contaminated plume, is shown in Figure 15.3b. In such situations, it will be necessary to contain the plume either by installing barrier walls and pumping the waste to the surface for treatment, or by sinking a discharge well to reverse the flow of water. A third option is that the chemical is denser than water and is immiscible, in which case it would be expected to lie on an impervious layer somewhere under the aquifer, as shown in Figure 15.3. Commonly, wells are drilled around the contaminated site so that the groundwater flow can be reversed or the groundwater can be contained in the area, as discussed in Chapter 10. Once the contaminated water is extracted, it must be treated, and the choice of treatment obviously depends on the nature of the problem. If the contamination is from hydrocarbons such as trichloroethylene, it is possible to remove this with activated carbon. Some type of biological treatment system or distillation process may also be used. If the contamination is from metals, then a precipitation or redox process may be used. Some soils may be so badly contaminated that the only option is to excavate the site and treat the soil ex situ. This is usually the case with PCB contamination because no other method seems to work well. The soil is dug out and usually incinerated to remove the PCBs and then returned to the site or landfilled. Depending on the contaminant, biodegradation in reactors or piles may be used. Excavation and landfilling are also commonly used to meet construction and real estate transaction schedules. In situ treatment of the contaminated soil involves the injection of either bacteria or chemicals that will destroy the offending material. If heavy metals are of concern, these can be tied up chemically or fixed so that they will not leach into the groundwater. Organic solvents and other chemicals can be degraded by injecting freeze-dried bacteria or by making conditions suitable for indigenous bacteria to degrade the waste, e.g., by injecting air and nutrients. Microorganisms that are able to decompose materials that were previously thought to be refractory or even toxic have been found. 1522 Treatment of hazardous wastes. The treatment of materials deemed hazardous is obviously specific to the material and the situation. Therefore, there are a number of alternatives that engineers may consider in such treatment operations. Chemical treatment is commonly used especially for inorganic wastes. In some cases, a simple neutralization of the hazardous material will render the chemical harmless. In other cases, oxidation is used, such as for the destruction of cyanide. Ozone is often used as the oxidizing agent. In a case wherein heavy metals must be removed, precipitation is the method of choice. Most metals become extremely insoluble at high pH ranges, so the treatment consists of the addition of a base, such as lime or caustic, and the settling of the precipitate, similar to the lime soda softening process described in Chapter 10. Other physical-chemical methods employed in industry include reverse osmosis, electrodialysis, solvent extraction, and ion exchange. If the hazardous material is organic and is readily biodegradable, most often the least expensive and most dependable treatment is biological, using techniques described in Chapter 11. The situation becomes interesting, however, when the hazardous material is an anthropogenic compound created by people. Because these combinations of carbon, hydrogen, and oxygen are new to nature, there may not be any microorganisms that can use them as an energy source. In some cases, it is still possible to find a microorganism that will use this chemical as a food source, and treatment would then consist of a biological contact tank in which the pure culture is maintained. Alternatively, it is now increasingly likely that specific microorganisms can be designed by gene manipulation to attack certain especially difficult to treat organic wastes. Finding the specific organism can be a difficult and arduous task. There are millions to choose from, so how would we know that Corynebacterium pyrogens just happens to like toxaphene, a particularly refractory organic pesticide? Secondly, often the pathway is convoluted and a single microorganism can only break down the chemical to another refractory compound, which would then be attacked by a different organism. For example, DDT is metabolized by hydrogenamonas to p-chlorophenylacetic acid, which is then attacked by various Arthrobacter species. Tests in which only a single culture is used to study metabolism would, therefore, fail to note the need for a sequence of species. One interesting development has been the use of co-metabolism to treat organic chemicals that were once considered biologically non-biodegradable. With this technique, the hazardous material is mixed with a non-hazardous and at least partially biodegradable material, and the mixture is treated in a suspended or fixed film bioreactor. And microorganisms apparently are so busy making the necessary enzymes for the degradation of the biodegradable material, the metabolite, that they forget that they cannot treat the toxic material, the cometabolite. The enzymes produced, however, will biodegrade both the chemicals. The addition of phenol to the soil, for example, will trick some types of microorganisms, such as fungus, into decomposing chlorophenol, even though chlorophenol is usually toxic to the fungus. One of the most widely used treatment techniques for organic wastes, however, is incineration. Ideally, hazardous waste incinerators produce carbon dioxide, water vapor, and inert ash. In actuality, no incinerator will achieve complete combustion of the organics. It will discharge some chemicals in the emissions, concentrate others in the bottom ash, and produce various compounds called products of incomplete combustion. For example, polychlorinated biphenyl PCBs are thought to decompose within the incinerator to highly toxic chlorinated dibenzofuran CDF, which, although organic, do not oxidize at normal incinerator temperatures. Despite these problems, hazardous waste incinerators must achieve high levels of removal efficiencies, often 99.99% or higher, which is commonly referred to as 4 nines. In some cases, removal efficiencies require 5 or even 6 nines. Example 15.2: a hazardous waste incinerator is to burn 100 kilograms of a PCB waste that is 22% PCB and 78% organic solvents. In a trial run, the concentration of PCB in the emission is measured as 0.02 grams and the stack gas flow rate is 40 mn. No PCB is detected in the ash. What removal efficiency, destruction of PCB, does the incinerator achieve? 1523 Disposal of hazardous waste. The disposal of hazardous waste is similar in many ways to the disposal of non-hazardous solid waste. Because disposal in the oceans is prohibited and outer space disposal is still far too expensive, the final resting place has to be on land. Deep well injection has been used in the past and is still the method of choice in the petrochemical industry. The idea is to inject the waste so deep into earth that it could not in any conceivable time reappear and cause damage. This is, of course, the problem. Once deep in the ground, it is impossible to tell where its final destination will be and what groundwater it will eventually contaminate. A second method of land disposal is to spread the waste on land and allow the soil microorganisms the opportunity to metabolize the organics. This technique was widely used in oil refineries and seemed to work exceptionally well. The U.S. EPA, however, has restricted the practice because there is little control over the chemical once it is on the ground. The method most widely used for the disposal of hazardous waste is the secure landfill. Such landfills essentially look like the RCRA Subtitle D landfills discussed in the previous chapter, only more so. Instead of one impervious liner, secure landfills require multiple liners. Liquid waste is banned. All waste must be stabilized or in containers. Similar to sanitary landfills, leachate is collected and a cap is placed on the landfill once it is complete. Continued care is also required, although the U.S. EPA presently requires only 30 years of monitoring. Most hazardous waste engineers agree that there is no such thing as a secure landfill and that eventually all the material will once again find its way into the water or air. What we are betting on, therefore, is that the wastes in these storage basins will degrade on their own, or that the storage basins will eventually be dug up and the material treated. We find that it is inexpedient to do so today and leave this as a legacy to future generations. 15.3 Radioactive waste management. A special type of hazardous material emits ionizing radiation, and in high doses this radiation can be highly detrimental to human health. Environmental engineers do not usually get involved in radiation safety, which is a specialized field, but they nevertheless ought to be knowledgeable about both the risk and the disposal technology of radioactive materials. In addition to the U.S. EPA, the Nuclear Regulatory Commission and Department of Energy have authority over management of radioactive waste. The U.S. EPA is particularly involved when radioactive waste is mixed with RCRA hazardous waste, substances known as mixed wastes. 153. Ionizing radiation. Radiation is a form of energy due to the decay of isotopes. An isotope of an element has the same atomic number of protons, but a different mass number of neutrons and protons than the standard element. In other words, it has a different number of neutrons. Remember that the atomic number defines an element. For example, the atomic number of uranium is 92. Uranium-235, U-235, therefore, is an isotope of uranium, U-238. To regain an equilibrium, the isotopes decay by emitting protons, neutrons, or electromagnetic radiation to carry off energy. This natural spontaneous process is radioactivity. The isotopes that decay in this manner are called radioisotopes. The energy emitted by this decay that is strong enough to strip electrons and sever chemical bonds is called ionizing radiation. There are 4 kinds of ionizing radiation: alpha particles, beta particles, gamma or photon rays, and X-rays. Alpha particles consist of 2 protons and 2 neutrons, so they are the equivalent of the nucleus of a helium atom being ejected. Alpha particles are quite large and do not penetrate material readily, therefore they can be readily stopped by skin and paper and are not of major health concern unless they are taken internally, in which case they can cause a great deal of damage. The decay changes the parent element into a different element known as a daughter product. Beta radiation results from an instability in the nucleus between the protons and neutrons. Having too many neutrons, some of the neutrons decay into a proton and an electron. The proton stays in the nucleus to reestablish the neutron-proton balance, while the electron is ejected as the beta particle. The beta particle is much smaller than the alpha particle and can penetrate living tissue. However, about 1 centimeter of material will shield against beta particles. Beta decay, as with alpha decay, changes the parent into a new element. Both the alpha and beta decay are accompanied by gamma radiation, which is a release of energy from the change of a nucleus in an excited state to a more stable state. The element thus remains the same, and energy is emitted as gamma radiation. Related to gamma radiation are X-rays, which result from an energy release when electrons transfer from a higher to a lower energy state. Both types of radiation have more energy and penetrating power than the alpha and beta particles, so a dense material, such as lead or concrete, is required to stop them. All radioactive isotopes decay and will eventually reach stable energy levels, as introduced in Chapter 5. The decay of radioactive material is first order in that the change in the activity during the decay process is directly proportional to the original activity present, or half-lives of radioisotopes can range from the almost instantaneous e.g., polonium-212 with a half-life of 3.3x107s to very long e.g., carbon-14 with a half-life of 5,570 or table 15.4. The half-life is characteristic of an isotope. Therefore, if you know the isotope, you know the half-life and vice versa. Example 15.3. What will be the activity after 5 days of a 1.0 Curie, so Rn 222 source? A psi and a Becquerel BQ are measures of the emission, or decay, rate. 1532 Risks associated with ionizing radiation soon after Wilhelm-Röntgen. 1845. 1923 Discovered X-rays. The detrimental effect of ionizing radiation on humans became known, and the emergent field of health physics set about creating safety standards, with the assumption of identifying the level of exposure that would be safe. They figured that there had to be a threshold in exposure below which no effects would be found. Over about 30 years of studying both acute and chronic cases, they found that their threshold kept getting lower and lower. While small amount of radiation above background levels have been found to stimulate biological systems, a process known as radiation hormesis, they finally concluded that assuming there is no threshold in radiation is the safest course of action. The exposure of human tissue to ionizing radiation is complicated by the fact that different tissues absorb radiation differently. To get a grip on this, however, we must first define some unit of energy that expresses ionizing radiation. Historically, this was established as the Röntgen, defined as the exposure from gamma or X-ray radiation equal to a unit quantity of electrical charge produced in air. The Röntgen is a purely physical quantity measuring the rate of ionization. It has nothing to do with the absorption or effect of the radiation. Different types of radioactivity can create different effects, and not all tissues react the same way to radiation. Thus, the REM or Röntgen equivalent man was invented. The REM takes into account the biological effect of absorbed nuclear radiation, so it measures the extent of biological injury. The REM, in contrast to the Röntgen, is a biological dose. When different sources of radiation are compared for possible damage to human health, REMs are used as the units of measurement. Modern radiological hygiene has replaced the Röntgen with a new unit, the gray Gi, defined as the quantity of ionizing radiation that results in absorption of 1 joule of energy per kg of absorbing material. But the same problem exists in that the absorption may be the same, but the damage might be different. Hence, the sievert SV was invented. A is an absorbed radiation dose that does the same amount of biological damage to tissue as 1 Gi of gamma radiation or X-ray. 1 SV is numerically equal to 100 rem. The damage from radiation is chronic as well as acute. Radiation poisoning, as witnessed in the Hiroshima and Nagasaki bombings at the end of World War II, showed that radiation can kill within a few hours or days. Over time, lower levels of radiation exposure can lead to cancer and mutagenic effects, and these are the exposures that are of most concern to the public. The sources of exposure of humans to radioactivity can be classified as involuntary background radiation, voluntary radiation, involuntary incidental radiation, and involuntary radiation exposure due to accidents. Background radiation is due mostly to cosmic radiation from space, the natural decay of radioactive materials in rocks terrestrial, and radiation from living inside buildings internal. A very special kind of background radiation is radon. Radon-222 is a natural isotope with a half-life of about 3.8 days and is the product of uranium decay in Earth's surface. Radon is a gas, and because uranium is so ubiquitous in soil and rock, there is a lot of radon present. With its relatively long half-life, it stays around long enough to build up high concentrations in buildings. Its decay products are known to be dangerous isotopes that, if breathed into lungs, can produce cancer. The best technique for reducing the risk from radon is to first monitor to see if a problem exists and, if necessary, ventilate the radon to the outside, figure 15.4 on the next page. All entry radiation can occur from such sources as diagnostic X-rays. One dental X-ray can produce hundreds of times the background radiation, and these should be avoided unless critically necessary. Following the discovery of X-rays, called Roentgen rays everywhere in the world except the United States, the damaging effects of X-rays began to be discovered due to the early deaths of many of Roentgen's friends. Another source of voluntary exposure is from high-altitude flights in commercial airlines, where Earth's atmosphere is a good filter for cosmic radiation, but there is little filtering at high altitudes. Involuntary incidental radiation would be from such sources as nuclear power plants, weapons facilities, and industrial sources. While the Nuclear Regulatory Commission allows fairly high exposure limits for workers within these facilities, it is fastidious about allowing radiation off premises. In all probability, the amount of radioactivity produced in such facilities would be within the background. The fourth type of radiation exposure is from accidents, and this is a different matter. The most publicized accidental exposure to radiation has been from accidents or near accidents at nuclear power plants. The accident near Harrisburg, Pennsylvania, at the 3 Mile Island nuclear power facility was serious enough to bring to a halt the already staggering nuclear power industry in the United States. Following a series of operating errors, a large amount of fission products were released into the containment structure. The amount of fission products released to the atmosphere was minor, so at no time were the acceptable radiation levels around the plant exceeded. The release of radiation during this accident was so small, in fact, that it is estimated that it would result in one additional cancer death over the 80-kilometer radius surrounding the 3 Mile Island facility. This would be impossible to detect because within that radius there can be expected to develop over 500,000 cancers during the lifetime of the people living in the area. A much more far-reaching accident occurred in Chernobyl in the Ukraine. This actually wasn't an accident in the strict sense because the disaster was caused by several engineers who wanted to conduct some unauthorized tests on the reactor. The warning signals went off as they proceeded with their experiment, and they systematically turned off all the alarms until the reactor experienced a meltdown. The core of the reactor was destroyed, the reactor caught on fire, and the flimsy containment structure was blown off. Massive amounts of radiation escaped into the atmosphere, and while much of it landed within the first few kilometers of the facility, some reached as far as Estonia, Sweden, and Finland. In fact, the accident was first discovered when radiation safety personnel in Sweden detected unusually high levels of radioactivity. Only then did the officials of the former Soviet Union acknowledge that, yes, there had been an accident. In all, 31 people died of acute radiation poisoning, many by heroically going into the extremely highly radioactive facility to try to extinguish the fires. The best estimates are that the accident will produce up to 9,000 excess cancer deaths among the population in the Ukraine, Belarus, Lithuania, and the Scandinavian countries. But once again, this number is dwarfed by the expected total cancer deaths of 10 million during the lifetime of the people in these areas. The total radiation we receive is, of course, related to how we live our lives, where we choose to work, if we choose to smoke cigarettes, whether we have radon in our basements, and so on. 1532 Risks associated with ionizing radiation. As the U-237 decays, it produces a series of daughter isotopes that themselves decay until the rate and hence heat output are reduced. What is left over, commonly known as the fission fragments, represent the high-level radioactive material that requires cooling down, long-term storage, and eventual disposal. The long-term storage of high-level radioactive waste has been debated for decades. Over protests, a site in Nevada, at Yucca Flats, has been selected and is being prepared. Low-level radioactive waste should not represent a disposal problem, because the activity levels of these wastes are so low that they can be handled by direct contact. It would seem that, with judicious volume reduction such as incineration, any secure landfill would be adequate. The U.S. Congress passed the Low-Level Waste Policy Act in 1980 that stipulated that states form compacts so that each state will take its turn in providing a disposal facility for a certain time. Unfortunately, the very mention of the word radioactivity is enough to arouse public opinion and prevent the siting of these disposal facilities. 1533 Treatment and disposal of radioactive waste. The most important distinction to be made in radioactive waste disposal is the level of radioactivity emitted. While there appears to be an increasingly complex system of characterization for radioactive wastes, the broad classification is as high-level, intermediate-level, and low-level waste. High-level wastes occur mostly from the production of electric power, and these are identified by activities in the range of curies per liter. Intermediate-level wastes are produced by weapons manufacture, and although their activities are in the range of millicuries, the particular isotopes are long-lived, so these wastes require long-term storage. Low-level wastes, characterized as those with activities in the range of microcuries per liter, are produced in hospitals and research laboratories. In nuclear power plants, nuclear fission occurs when fissionable material, such as uranium-237, is bombarded with neutrons and a chain reaction is set up. The fissionable material then splits, hence the term fission, to release huge quantities of heat, used in turn to produce steam and then electricity. 15.4 Sustainable Materials Management. In the book Materials Matter, Kenneth Geiser identifies two strategies to support sustainable materials management. One involves developing ways to use less material to provide the same service to satisfy human needs, a process known as dematerialization. The second strategy, called detoxification, is used to lower the inherent hazard associated with chemicals used in products and industrial processes. Dematerialization means reducing the amount of material in a product without decreasing the quality of the service it provides. It reduces the flow of virgin materials into and through the industrial economic system. Strategies for dematerialization include reducing the weight or thickness of packaging materials, developing organic chemicals from biomass wastes rather than fossil fuels, and promoting recycling and secondary materials industries to keep material cycling in industrial loops rather than relying on virgin resources. A variation on dematerialization is rematerialization, switching to the use of materials that are inherently more sustainable rather than using less of the initial material. Designing products for repair, upgrade, and/or recycling supports the need for fewer resources and helps keep materials within the industrial economic system. Dematerialization as a strategy for sustainable materials management is challenged by the growing demand for materials, even if at a decreased per capita rate, through growth. An example of dematerialization is the soda club system. The strategy of detoxification includes substituting benign alternatives for problematic chemicals, e.g., substituting rapidly biodegradable surfactants for surfactants that degrade into toxic byproducts, phasing out the use of chemicals of concern such as persistent bioaccumulative and toxic substance PETs, generating toxics on demand or just in time to avoid the need for storage and transportation, designing new chemicals and materials that are benign with respect to human health and the environment. The design of such chemicals is the domain of the growing field of green chemistry. Green chemistry has emerged as an effective strategy for detoxification and as a means to design chemical products and processes to create sustainable materials and products. Example 15.4 Many people enjoy drinking club soda, also called sparkling water, carbonated water, or seltzer water. The Soda Club system requires the purchase of one 1L bottle, a refillable Coke cartridge that will produce 110 ml of soda, and the housing that holds it. The bottle is refillable until it becomes cracked or otherwise fails. To make club soda, you fill the bottle with your own tap or filtered water, screw the bottle into the Coke cartridge housing, and then press a button to release Coke into the bottle. After a few moments, a loud noise generated from pressure in the bottle indicates that the liquid is adequately carbonated and ready to drink. Assume that total cost to get started is $79 and includes a Coke cartridge, the bottle, and the housing. When the Coke cartridge is empty, you can return it to the point of purchase to refill it for $15. Assume that your family currently drinks 6 ml of club soda each week at $1.50 per bottle and that you purchase them by the case at 12 bottles per case and one trip to the grocery store per case. Compare the cost, transportation footprint, and waste generated from purchasing individual bottles of club soda to use of the Soda Club system. 1541 Green chemistry. Green chemistry is the design of chemical products and processes that reduce or eliminate the use and generation of hazardous substances. The focus of green chemistry is on design because decisions are made at the level of design that impact the performance, toxicity, and fate of chemicals. The focus on hazard rather than risk is also significant. Risk is a function of hazard and exposure. The term hazard is used broadly to include any of the attributes inherent in a chemical if you are exposed to it. Hazard may include acute human toxicity, chronic human toxicity, i.e., carcinogenicity, reproductive or developmental toxicity, skin or eye irritation, sensitization of the skin or respiratory system, ecological toxicity, safety issues, e.g., explosiveness or flammability, potential for damage to the ozone layer, destruction of biological habitat, and more. Green chemistry addresses risk but from a different angle than conventional practices. Traditional risk management focuses on controlling risk by controlling the potential for exposure. However, exposure controls can and do fail. Failures to control exposure have led to deadly incidents, such as in Bhopal, India, when a release of methyl isocyanate killed thousands of people in a nearby town. Because methyl isocyanate is highly hazardous, when the exposure controls failed and released a chemical, it created a high-risk situation. By addressing and reducing the inherent hazard of a chemical, it is possible to reduce risk and even to eliminate the need for exposure controls, which can be very expensive. Green chemistry is a tool for chemists, chemical engineers, and others who design chemicals and materials to help move society toward the goal of sustainability. The wisdom behind the green chemistry approach has been gaining popularity in recent years, and we are now seeing the emergence of policy and legislation to support green chemistry. In the United States, Michigan's governor issued a Green Chemistry Executive Order. California is creating a policy platform called the Green Chemistry Initiative to support green chemistry and cradle-to-cradle design, and in the U.S. Congress, Senate Bill 2669, the Green Chemistry Research and Development Act of 2008, was introduced. Several examples of green chemistry follow to illustrate how materials can be designed to be environmentally compatible and to fit within a sustainable materials system. These examples are derived from entries to and winners of the Presidential Green Chemistry Challenge Awards program, the only presidential-level chemistry award program in the United States. In 1998, Rome and Haas Company won a Presidential Green Chemistry Challenge Award for designing the marine antifoulant called C9. Fouling, the unwanted growth of plants and animals on a ship's surface, costs the shipping industry approximately $3 billion a year. A significant portion of this cost is the increased fuel consumption needed to overcome hydrodynamic drag. The main compounds historically used worldwide to control fouling are based on organoids, such as tributyltin oxide (TBTO). While they are effective at preventing fouling, they are toxic and persistent in the environment. The negative environmental effects associated with TBTO include acute toxicity, bioaccumulation, decreased reproductive viability, and increased shell thickness in shellfish. Rome and Haas Company sought to develop an antifoulant that would protect ships from fouling by a wide variety of marine organisms without causing harm to non-target organisms. Company scientists selected compounds from the 3-isothiazolone class. Specifically, 45-dechloro-2-enokyl 4-isothiazolone 3,1 was selected because it was found to be effective and to degrade very rapidly in seawater, and even faster in sediment. While TBTO is considered highly bioaccumulative, C9 does not bioaccumulate at all. Both TBTO and C9 are acutely toxic to marine organisms, which is a desirable characteristic of a marine antifoulant, but C9 antifoulant degrades rapidly and is not chronically toxic. Thus, the chemical does its job but does not cause harm beyond its immediate function. TBTO persists and bioaccumulates in the environment so that it continues to have toxic effects. DE and Bioscience Corporation received a Presidential Green Chemistry Challenge Award in 2001 for the product Messenger R. Messenger R is based on a class of non-toxic naturally occurring proteins called harpins. Harpin proteins trigger the natural defense systems of plants to protect themselves against diseases and pests. It also activates certain plant growth systems without altering the plant's DNA. When applied to crops, harpins support plant health, resulting in increased plant biomass, photosynthesis, nutrient uptake, and root development. Ultimately, such increases lead to greater crop yield and quality of product. Estimated crop losses from pests are estimated at $300 billion worldwide. Growers have typically pursued two strategies to limit economic losses and to increase yields. 1. Using traditional chemical pesticides, or 2. Growing crops that are genetically engineered for pest resistance. Each of these approaches has negative consequences, particularly on non-target organisms and in terms of public perception. In contrast, harpins have been shown to have virtually no adverse effect on any of the organisms tested, including mammals, birds, honeybees, plants, fish, aquatic invertebrates, and algae. Because it is a fragile molecule, it is degraded rapidly by UV and natural microorganisms. It has no potential to bioaccumulate, and it will not contaminate surface or groundwater resources. Unlike most agricultural chemicals, harpin-based products are produced in a water-based fermentation system that uses no harsh solvents or reagents, requires only modest energy inputs, and generates no hazardous chemical wastes. From the life cycle perspective, harpin is made via green chemistry processes, has low hazard characteristics, and supports sustainable agriculture. In 2008, Battelle and its partners, Advanced Image Resources, and the Ohio Soybean Council received the Presidential Green Chemistry Challenge Award for developing a soy-based toner. Laser printers and copiers use over 200 million kg of toner each year in the United States alone. Traditional toners fuse so tightly to paper that they are difficult to remove from waste paper for recycling. They are also made from petroleum-based starting materials like styrene acrylates and styrene butadiene. Battelle and its partners developed a soy-based toner that performs as well as traditional ones but is much easier to remove. The new toner technology can save significant amounts of energy and allow more paper fiber to be recycled. The new toner will be sold under the trade names Biorez R and Resolution R. Once commercial, it will provide users with seamless printing and copying using soy-based chemistry. There are many more examples of green chemical innovation. Some of them reflect changes in chemical processes, such as eliminating hazardous solvents or using catalysts to eliminate the number of steps in a chemical synthesis. Other examples illustrate the generation of new chemicals to replace chemicals of concern, and others demonstrate innovation by generating desired chemicals from bio-based feedstocks rather than from petroleum-based feedstocks, which have been the backbone of organic chemistry. Green chemistry is important because it demonstrates that it is possible deliberately to design new molecules in chemical processes with the intent to reduce overall hazard and to produce sustainable products and processes. Although technology is not a panacea for society. According to Arnulf Grubler in his book Technology and Global Change, through technology humanity has for 300 years increasingly liberated itself from the environment. The job is not yet complete as billions of people continue to be excluded from the benefits of technology. The next immediate task is to assure their inclusion. But what next? We need a European vision, a new technology manifesto to set our goals for the 21st century. Grubler argues that the task ahead is to progressively liberate the environment from adverse human interference. For this century-long journey, we will need more technology, not less. As the world's population grows to 10 billion or more, we recognize that nature cannot be shielded perfectly from human intervention any more than we can be shielded perfectly from nature, but technological change can relax our grip and lighten our tread on the natural world. Our choices are constrained by what already exists in the environmental legacy of the past, but over the long term, the capacity for social choices to shape technology is endless. 1542 Pollution prevention. A subset but more widely practiced aspect of sustainable materials management is pollution prevention. The EPA defines pollution prevention as the following: the use of materials, processes, or practices that reduce or eliminate the creation of pollutants or wastes at the source. It includes practices that reduce the use of hazardous materials, energy, water, or other resources, and practices that protect natural resources through conservation or more efficient use. In the widest sense, pollution prevention is the idea of eliminating waste, regardless of how this might be done. It is the same concept here as in the management of municipal solid waste as described in Chapter 14, but the incentives for using it are much greater. Originally, pollution prevention was applied to industrial operations with the idea of either reducing the amount of the wastes being produced or changing their characteristics to make them more readily disposable. Many industries changed to water-soluble paints, for example, thereby eliminating organic solvents, cleanup time, etc., and often ended up saving considerable money. In fact, the concept was first introduced as pollution prevention pays, emphasizing that many of the changes would actually save the companies money. In addition, the elimination or reduction of hazardous and otherwise difficult wastes has a long-term effect. It reduces the liability the company carries as a consequence of its disposal operations. With the passage of the Pollution Prevention Act of 1990, the EPA was directed to encourage pollution prevention by setting appropriate standards for pollution prevention activities, assist federal agencies in reducing wastes generated, work with industry to promote the elimination of wastes by creating waste exchanges and other programs, seek out and eliminate barriers to the efficient transfer of potential wastes, and to do this with the cooperation of the individual states. In general, the procedure for the implementation of pollution prevention activities is to recognize a need, assess the problem, evaluate the alternatives, implement the solutions. Contrary to the attitude towards most pollution control activities, industries generally have welcomed this governmental action, recognizing that pollution prevention can, and often does, result in the reduction of costs to the industry. Thus, a recognition of the need quite often is internal, and the company seeks to initiate the pollution prevention procedure. During the assessment phase, a common procedure is to perform a waste audit, which is nothing but the black box mass balance, using the company as the black box. Consider example 15.5. Example 15.5. A manufacturing company is concerned about the air emissions of volatile organic carbons box. These chemicals can volatilize during the manufacturing process, but there is no way of estimating just how much or which chemicals. The company conducts an audit of 3 of their most widely used VOCs with the following results. The average influent flow rate to the treatment plant is 0.76 ms. Once we know what and where the problems are, the next step is to figure out useful options. These options fall generally into 3 categories: operational changes, material changes, process modifications. Operational changes might consist simply of better housekeeping, plugging up leaks, eliminating spills, etc. A better schedule for cleaning as well as segregating the waste streams might similarly yield a large return on a minor investment. Material changes often involve the substitution of a chemical that is less toxic or requires less hazardous materials for cleanup than another. The use of trivalent chrome for chrome plating instead of the much more toxic hexavalent chrome has found favor, as has the use of water-soluble dyes in paints. In some instances, ultraviolet radiation has been substituted for biocides in cooling water, resulting in better quality water and no waste cooling water disposal problems. In one North Carolina textile plant, biocides were used in air washes to control algal growth. Periodic blowdown and cleaning fluids were discharged to the stream, but this discharge proved toxic to the stream, so the state of North Carolina revoked the plant's discharge permit. The town would not accept the waste into its sewers, rightly arguing that this may have serious adverse effects on its biological wastewater treatment operations. The industry was about to shut down when it decided to try ultraviolet radiation as a disinfectant in its air wash system. Fortunately, they found that the ultraviolet radiation effectively disinfected the cooling water and that the biocide was no longer needed. This not only eliminated the discharge, but it eliminated the use of biocides altogether, thus saving the company money. The payback was 1.77 years. 5 process modifications usually involve the greatest investments but can result in the greatest rewards. For example, countercurrent wash water use instead of a one-through batch operation can significantly reduce the amount of wash water needing treatment, but such a change requires pipes, valves, and a new process protocol. In industries wherein materials are dipped into solutions, such as in metal plating, the use of drag-out recovery tanks, an intermediate step, has resulted in saving plating solution and reducing waste generated. In any case, the most marvelous thing about pollution prevention is that most of the time the company not only eliminates or greatly reduces the discharge of hazardous wastes, but it also saves money. Such savings are in several forms, including, of course, the direct savings in processing costs, as with the ultraviolet disinfection example above. But there are other savings, including the savings in not having to spend time on submitting compliance permits and suffering potential fines for noncompliance. Future liabilities weigh heavily where hazardous wastes have to be buried or injected. Additionally, there are the intangible benefits of employee relations and safety. And of course, finally, there is the benefit that comes from doing the right thing, something not to be sneezed at. In hazardous waste management, doing the right thing often involves the elimination of a potential hazard for future generations. Much has been written about this commitment. Do we indeed owe anything to these yet-to-be-born people? 15.5 Hazardous waste management and future generations. Why should we even worry about all that? Is it not true that we will certainly personally never be affected adversely by hazardous wastes, and it is unlikely even that any of our children will suffer from inadequate disposal of these materials. Why are we so concerned with the future and with future generations? RCRA requires waste facility operators to provide perpetual care for depositories. However, this is defined as a period of only 30 years. Perpetual care means only one half of a generation. The primary hazardous waste law in the United States apparently does not care about future generations, so why should we? After all, these people do not exist, nor might they ever exist. They are not real people, and ethics can apply only to interactions between real people. Also, we don't know what the future will bring. We cannot assume that future people will have the same preferences or needs, therefore we cannot predict the future. We may be well-intentioned but utterly wrong. Also, history teaches us that, at least to this point in the existence of civilization, each successive generation has been better off than the previous one. We have better health, better communication, better food, more time, and greater opportunity for personal growth and the enjoyment of the quality of life than ever before. Because we can expect future generations to continue this trend and to have an ever-improving life, we should do nothing for them. Besides, as the old saying goes, what has posterity ever done for me? So it may be very noble to take account of future generations, but there appears to be no basis for the claim that we ought to do so. For all these reasons, then, it may seem that there is nothing wrong with our deciding to generate nuclear wastes in order to enjoy the benefits of electricity, or using up the non-renewable resources such as oil, or interpreting our obligations of perpetual care as extending for only 30 years. Planning for hazardous waste management, or for anything else, therefore, needs to take into account only the interests of present generations. But are there not counter-arguments? Surely we cannot just blunder along hedonistically without concern for future humanity. What reasons can we give for a concern for future generations? Alistair Gunn argues that there are indeed strong reasons for our obligations to future generations. First, it is true that, by definition, future generations do not exist, but that does not mean we cannot have obligations to them. Certainly, we do not have the kinds of one-on-one obligations that identifiable individuals have to each other. For instance, debts and promises can be owed only by one person to another, but we also have obligations to anyone who might turn out to be harmed by our actions, even though we do not know their identity. Gunn uses an analogy of a terrorist who plants a bomb in a primary school. Plainly, the act is wrong and in breach of a general obligation not to cause or recklessly risk harm to our fellow citizens. This is so even though the terrorist does not know who the children are or even whether any children will be affected. The bomb may not explode or may be discovered in time, or the school may be closed down. It is equally wrong to place a time bomb set to go off in the school in 20 years' time, even though any children that may be in the school when it goes off are not yet born. An unsafe hazardous waste dump may be seen as analogous to a time bomb. The analogy is not perfect because the owners of the chemical company do not set out to kill children, but intent is not necessary if there is good reason to believe that an action would cause harm. A person throwing a cherry bomb into a crowd may not intend to harm anyone, but if harm does occur, he or she is as guilty as if the original intent was to hurt people. Whether the people harmed are here today or will be here in the future is irrelevant. It is the harm that counts, and causing the harm is unethical. The counter-arguments for the second claim, that we will never know what future generations will value, state that, yes, we do, in fact, have some pretty good ideas of what they will not value. For example, it is highly unlikely that they will value cancer or AIDS or polluted groundwater. We can expect future generations, in fact, to be much more similar to ourselves than different from ourselves. To suggest that we should contaminate Earth because we don't know what future people will value is not a valid argument. The third object ion to caring about future generations is that, because they will be better off than we are, there is no need to worry about their well-being. This makes no sense because the economic condition of a person is irrelevant to the harm that might be done. It is not legal or ethical to rob a person just because he or she might be wealthy. Besides, there is no guarantee that enhanced technology will bring continued greater well-being. There are more starving people in the world today than ever before, and the continued growth of human population and the destruction of natural habitats may well bring the world into an economic and ecological collapse. We have stretched the carrying capacity of Earth to its limits, and we have no guarantee that technology or social and political progress will enable us to even have a future generation, much less be able to care for it. As Gunn concludes, we have an obligation to avoid creating detrimental environmental conditions for future generations that we do not want to create for ourselves. This means that in terms of waste management, it is necessary to develop methods for very long-term, acceptably safe storage and, more importantly, steadily reducing the quantity, toxicity, and persistence of the wastes we produce so that acceptably safe management becomes possible. Further, there seems little doubt that future generations will appreciate clean air and water, adequate wilderness areas, and the preservation of natural monuments, and that this is an obligation of our present generation.